Good afternoon. So this talk is focused towards practical differentially private convex optimization, and this is joint work with my wonderful co-authors that are listed on the screen. So let me start by briefly stating the contributions of this work. So the first contribution is that we design a new private algorithm, which we call approximate minima perturbation, or AMP for short. It is designed towards being deployable in practice, and it has many advantages. I'll describe in detail soon. The second contribution is that we conduct a broad empirical study of the state-of-the-art techniques in the field. We do this over 2 models and 13 datasets, 4 of which are high dimensional. And all of our benchmarks, as well as the code for our technique, are open source and available on the following link. So in this talk, I'll start by providing some motivation of why do we need privacy for learning. Then I'll cover some background. First, I'll introduce what is differential privacy and give a quick refresher on convex optimization. Then I'll introduce our technique, AMP, and I'll conclude by presenting the results of our study. So that's the plan. Before I dive in, let me first define the framework that we'll operate in. So we are given a sensitive data set D that is given as input to a learning procedure A, which gives out an output model. You can think of the output model theta hat as a vector of weights for some network. Many recent works have shown that these models can leak information about the training data. These can be split into 2 broad categories. For example, in membership inference attacks, an adversary can confidently predict whether any sample was introduced in the training process by just accessing the output model theta hat. So without even looking at the data set, by only accessing the output model, the adversary can predict membership inference. How do we prevent such leaks? So differential privacy has been recently used as a gold standard to prevent such leakage. Let's start by intuitively understanding what does the notion mean. So we have a data set D comprising of several members that is input into a randomized algorithm A, which gives out some model theta. Since A is randomized, it has some distribution over the set of outcomes. So here on the x-axis, I'm denoting the model space. Each point represents some model theta hat. And the y-axis denotes the probability of algorithm A outputting that particular model when the input is dataset D. Imagine that I change one person from the input dataset. So I've replaced Om by Felix. Let me denote this dataset by D prime. Since the dataset changes, the distribution over the outputs can also change, which is represented by the red plot. What differential privacy guarantees is that the change for any particular output is small. So in some sense, the algorithm outputs each particular model with about the same probability, whether D or D prime was used, and effectively it does not depend much on any particular individual's data. The definition is characterized by 2 parameters, epsilon and delta. It has a mathematically precise formula, but in the interest of time, I'll just say that epsilon bounds the multiplicative change in the probabilities, and it is standard to consider epsilon as a small constant, whereas delta bounds the additive change, and typically it vanishes with the data size n. It's standard to consider delta as 1 over n squared. The important thing is as these parameters go down, the level of privacy goes up. A quick intro to convex optimization and also to formalize the notation. We have a data set D that consists of n samples from some population. We are given a loss function L that's parameterized by a model and a data set. And the condition is the loss function is convex in the first parameter, theta. The goal is to output the minima of this loss function. So the goal is to output theta hat such that it minimizes the loss. And this has many applications ranging from machine learning, deep learning, recommendation systems, many more. So there has been a lot of work in the area of differentially private convex optimization. There is a technique called objective perturbation, which, as the name suggests, it perturbs the input loss function. There are a couple of techniques that add noise within the training procedure itself. And there are a couple more that deal with the output model. They perturb the output. However, what is important to note is that two of these techniques require the exact minima of the loss function that you are optimizing over. And as we know, this is never guaranteed in practice. You can not guarantee the exact minima. Whereas the other techniques require some custom optimizer. So if you already have some tuned optimizer using some infrastructure in place, these techniques might not be the best suited. This motivates us to design what we call AMP. Here we are given a data set D, and I'll denote the privacy parameters by B corresponding to some budget. In addition, this technique requires what is called a gradient norm bound. I'll denote it by gamma. I'll describe its significance soon. So the technique is very simple. It can be described in 4 steps at high level. So here's how it goes. So the first step is to split the privacy budget into 2 parts. Using the first part, you add some regularization to the loss function. And for the members that are familiar with objective perturbation, this step is very similar to that technique. So effectively, now the loss function at our disposal looks something like this. We denote it by L_priv. Consequently, the minimizer also changes. We'll denote it by theta_priv. So now you can use your favorite optimizer to optimize over this perturbed loss. But when do you stop? This is where the parameter gamma comes in. So gamma defines a region around the minimizer where the norm of the gradient is bounded from above by gamma. Note that the norm of the gradient at the minimizer theta_priv is 0, so around it should be very small. So you continue optimizing until you reach any point within this region. So let's denote it by that point by theta approx, as it is an approximate minima of the perturbed loss. What you do is you add some noise using the second part of your privacy budget and release that model. So this is the output of the algorithm. We also provide formal utility guarantees for this technique. But rather than trying to explain you this beautiful slide, I'll just provide the takeaways. So one major advantage of this technique is that it can leverage any off-the-shelf optimizer. We don't place any restrictions on the optimizer used. It also works for all standard convex loss functions. Most of the techniques in prior work apply to only GLMs, or generalized linear models. Next, if you set gamma small enough, the gradient norm bound small enough, then the utility guarantee of this technique is on the same order as objective perturbation. Objective perturbation has the best asymptotic utility guarantees in the field, but it requires the exact minimizer, which is not practical. In addition to it, our technique also has a better dependence on the dataset size n, as compared to private permutation-based stochastic gradient descent. That is the state of the art in output perturbation. So you have to set gamma small enough to obtain this guarantee. What we see in our experiments is that gamma equal to 1 over n squared is very easily achievable, and like only using standard Python libraries. So you can hope for much smaller gamma as well. So next, I will talk about the second contribution, which is the empirical evaluation. We conduct our evaluation over 13 data sets that we categorize into 3 buckets: low dimensional, high dimensional, and real world data sets that have been obtained by a collaboration with Uber. So here the categorization is if the number of samples is much larger than the number of features, we say it is low dimensional. If it is comparable, we say it is high dimensional. The algorithms we evaluate include AMP, 2 of the techniques that add noise during the training process, and 2 techniques which are practical variants of output perturbation. One important point to note is that all of these techniques have some hyperparameters that need to be tuned for performance to be good. This involves some cost in itself that has to be taken into account. And so we also provide a hyperparameter-free variant of AMP. Basically, the only hyperparameter in our technique is how you split the privacy budget within the technique. And we provide a schedule for doing this by only evaluating it on synthetic data sets. So you have no cost to privacy. We also compare all the techniques with a non-private baseline. That is the technique which provides the best performance without considering privacy. So what is the experimental procedure? We consider 2 loss functions. In this talk, I'll focus on logistic regression. We first split the input data set we randomly split it into a training and testing set. We fix one of the privacy parameters delta to 1 over n squared, and we vary epsilon from 0.01, which is very high privacy, to 10, which is a lower level. We tune each algorithm and then report the mean accuracy and standard deviation over 10 independent runs. We report the accuracy over the test set. Note that this tuning does not apply to hyperparameter-free AMP. So let's start by looking at the results. So here, what I'm showing is the results on the synthetic data set that is low dimensional. On the x-axis, you have epsilon, which goes from a very high privacy level to a lower level. On the y-axis, you have the accuracy of the test set. The blue plot on the top represents the non-private baseline. And it's difficult to see the different algorithms in this plot as they're very crowded together. Next, I'll show results for high-dimensional synthetic data set. Here, what we do is we generate data that is actually low rank but high-dimensional. And here we see that private Frank-Wolf, which is the pink plot, it beats the other algorithms by a wide margin. And one of the reasons is it is designed to operate well on sparse data. And over these 2 data sets is where we tune hyperparameter-free AMP, which is the green plot. So next, I'll show some of the results on high-dimensional data sets, namely RealSim and RCV1. Here is where it is clearer that both variants of AMP, even the hyperparameter-free version, performs better than all the other tuned algorithms. So the orange plot denotes AMP, and the green one denotes hyperparameter-free AMP. And they almost always provide the best performance. Next are some results on real-world use cases, where these are large data sets. They have millions of samples. And the first observation here is that many prior works have theorized that differential privacy can act as a regularizer. And in dataset 1, we see that the best private algorithms, almost always outperform the non-private one. Also notice that since we have millions of samples, the x-axis, the range of the x-axis changes. On dataset 1, it's just 1/20th of a percent, whereas it's still pretty much small in the other dataset. We also see that all algorithms basically show a smaller variance, and the accuracy of AMP is very close to the non-private baseline, even for the lowest privacy level we consider. So I'd like to conclude by giving a summary. One observation in our study that we show through our experiments is that if you have a large data set, the cost of privacy is very low. We also see that AMP almost always provides the best accuracy, and it is designed to be easily deployable in practice. In addition to this, it also has a hyperparameter-free variant, which is end-to-end differentially private, and it is competitive with the tuned versions of the state-of-the-art algorithms. And finally, we open source our benchmark and our code. It's available on the following link. With that, thank you for your time, and I'd be happy to take questions.
Do you have any questions?
Thanks for the great talk. Sorry, this might be a naive question because I'm not an expert on differential privacy, but I was just wondering that, so what makes the decision of the epsilon value of 0.01 kind of adequate for privacy?
So it is majorly a policy decision as what epsilon value you should use. It should depend on the sensitivity of the data itself. For some tasks, value like 1 or 5 might be reasonable. For some sensitive tasks, a lower value might be reasonable. What we tried to show is that for basically the range of values that we've seen in the literature, so it's very rare to see even epsilon as low as 0.01. So we just show that how the privacy accounts for in this region.
So thanks for the answer. I have a follow-up question. So in the case where you have a real-world data set, like the Whooper data set, there are only 2 classes, right, for the classification task. So in that case, even for epsilon equals 0.01, isn't that just having 2 classes make it easy to distinguish the 2 cases where you have two different data sets that's neighboring?
So even though there are 2 classes, the guarantee holds over the complete sample. So if you notice, each sample has a lot of features, hundreds of features, and the privacy guarantee holds whether a particular vector is within the data set or not. And so in addition to the class, we also give privacy to the values of the features themselves.
Any other questions?
So you mentioned there are 4 steps in your approach. And you mentioned the second step is similar to some existing techniques. And the last one is just add noise. So what's the intuition here that your approach is better than all those optimized for specific, those techniques optimized for specific tasks? What's the magic here?
That's a very good question. So 2 of the techniques that are output perturbation and objective perturbation, they have really good utility guarantees, but the privacy holds only if you release the exact minimizer. So if you manage to reach the minimizer and release it, you get great guarantees. In practice, that's never guaranteed. So the thought process here was, what if you are very, very close to the actual minima? Can you get privacy guarantees for it? Because if it is close to the actual minima, it should perform well. So we add noise in the last step just to give privacy to that approximate minima. That's the high-level view.
Thanks.
Hi. I have a question. Do you use Convex to develop objective function in privacy guarantee or utility guarantee?
That's a very great question. So the privacy guarantees will depend here. Like you require some properties like smoothness, and basically it's not required for utility. It is. Yeah. For the privacy, you need some other guarantees to hold, but you'll be fine if you have like smoothness and strong. Yeah, it's mostly for the utility guarantees.
All right, any final questions? Okay, last question.
Hi, a very nice talk. Have you evaluated against any of the attacks that you mentioned in the beginning, like membership inference or model inversion?
So basically, what the notion of differential privacy gives you is a guarantee that you can avoid inference, for example, and how much the attack will be successful will depend on the level of epsilon. So basically, inference is whether an adversary can distinguish whether a sample is there or not, and differential privacy is a mathematical guarantee to prevent precisely that. So I think other papers that concentrate on the attacks do carry an evaluation. We have not carried that.
So a small follow-up to that. To that question, the differential privacy guarantees on the output does not vary too much, but inference, membership inference, or the other inferences are guarantees on the input. So can you actually relate those two?
So the guarantees are you cannot deduce anything about the input from the
Well, the
output.
guarantee itself just says that the output cannot vary, but it doesn't say anything about what you can infer about the input.
So it's precisely that from seeing the output, you cannot deduce much about the input samples. So if you observe the output, you cannot confidently say whether my sample was in the data set or not.
So this is more than just the original differential privacy definition that you're sort of inferring a little bit more from that.
No, this is exactly the
Okay,
definition.
maybe I'll talk to you after.
Yep, I'll be happy to.
Let's thank Om one more time.
Thank you.